Okay, welcome everybody. This is the Electrical Engineering Computer Sciences Department Colloquium. We're running at a different time than usual, but thanks for being here, and those of you online, welcome. It's my great pleasure to introduce our speaker today, Vahid Vahedi from Lam Research Corporation. And he is the Senior Vice President, Chief Technology Officer, and Sustainability Officer at Lam. So he's responsible for driving all the innovation breakthroughs and as well as looking after sustainability programs to get to net zero, which is a terrific goal. Vahid has over 30 years of experience in the industry, and he is a true gold bear. He has all of his bachelor's, master's, and PhD degrees from Berkeley. He graduated here. I won't tell you when. He looks, he's a young-looking guy, and I don't want to tell you when he got his degree. But anyway, he's been a great supporter of the department ever since, and he spends a lot of time here at Berkeley and helps us out in many different ways, and including being today's speaker. He's going to talk about the future of semiconductors, and he's going to go all the way from atomic precision to AI. So, welcome, Vahid.
Thank you. Thank you, Jeff. Thank you, ECS, for extending the invitation. It's a pleasure to be here, and it's great to share some of my personal experiences at Lam and in industry, but really I would like to talk more about how AI is accelerating the roadmap for semiconductor technology and the grand challenges that we see. These grand challenges where we need a lot of collaborations with research outfits and academia to be able to come up with new innovations, to be able to get us to where we need to go. So, as Jeff said, I graduated actually in '93 from UC Berkeley. I joined Lam Research in 1995. That was my badge. That was my picture 30 years ago when I joined. I joined in an organization that at that time was the CTO organization, as I joined as a process engineer after getting my degree here. And over the years at the company, I had different responsibilities. I ran the Etch product group, the business unit, for many, many years. And about 2 years ago, I took the CTO role and looking to see how we can get the company to the next chapter and through the next challenges that we see. So certainly it should be no surprise for any of you in here that semiconductors are fueling acceleration of innovations. When you look at the history, really over the past, I would say 6 decades, we have seen a significant acceleration in the pace of innovation around the industry. And a lot of that is really fueled by semiconductors. If you pick up any devices today, mobile or others, you see lots and lots of microchips in it. At the heart of each one of those microchips are devices, transistors, resistors, capacitors that are actually built by plasma etch equipments or by overall wafer fab equipment makers. So the wafer fab equipment makers are behind in the heart of every device that you carry today. We're in everything that you run today. In making these processes, there is about 600 to 800 steps, and through those, in these steps, you go through multiple steps of patterning, deposition the film that you want, patterning what you want, clean step, and go to the next cycle. And it's each one of these is becoming more and more critical and difficult than it was before. When you look at a very simple way of doing it, you're effectively depositing a film that you want to leave on the wafer. You use a lithography to transfer a pattern onto a mask that you want to do. You etch and you transfer that mask onto the layer below. You clean, you strip, and you go back to the next step. So, and this step repeats multiple times as you build your devices that you're doing. And then Lam Research today actually is a critical player in etch, deposition, strip, and clean, provider of equipments that we have for our customers to be able to do this. A little bit about Lam Research. The company has been around for 45 years. So 1980 was when it actually came on the scene. And at the time, it started out in Fremont, California. Today, the company is about 19,000 employees. And we have R&D centers in Fremont, California, about 40 minutes from here, in Oregon, in Europe, R&D facilities, as well as close to our customers in Korea, Taiwan, and other places. We have manufacturing sites all around the world. Last year, our revenue was about $16.2 billion, and our R&D budget was about $2 billion. Quite a bit of that work that we do, of that R&D budget, goes into fueling the foundation for the next generation innovations that we do. But part of that we also use for partnering with university and academia in funding projects in universities, academia, and research centers to be able to jumpstart and fuel the innovations that we need for the next node. So we have many active collaborations, and over the past, I would say since 2015, we have funded more than 200 projects around the world. And Berkeley is, of all the collaborations that we have, is very unique to us because, one, because of the proximity, two, because of the great faculty and students that are here, and three, because of the ecosystem that's around us as well as at Berkeley. Last year, actually earlier this year, Lam donated a tool to the Berkeley Nano Lab. It has multiple etch chambers on it. This system right now is in startup right here in the Nano Lab that is coming up. And we're actually actively talking to the faculty about expanding the collaborations that we have in the areas of sustainability, plasmas, novel materials, using AI and ML, as well as optical devices. So many potential opportunities for Lam and UC Berkeley to collaborate. Okay, coming back to AI. As you all know, the AI explosion is happening. It's probably one of the biggest industry transformational revolution that we're going through right now. And it's given the huge demand for AI, it's driving a lot of investments, wafer fab equipment investments for our customers. The requirements of AI, such as exploding AI model sizes, real-time inference, edge AI, the overall energy consumption that AI has, and the challenges with that as you try to scale it up, maintaining and the cost of increasing hardware needs that you have, effectively translates into requirements for next generation devices, such as scaling the GPUs to more and more compute power, higher speed and lower power DRAM for all the memory that you need in order to do those calculations, higher capacity NAND for storage, and transition really to 3D architecture in all segments of the market, whether it's in logic, whether it's in DRAM, or whether it's NAND. NAND has already transitioned into 3D, and today we build these 3D devices, and we stack up about maybe 300 to 400 tiers, and that will only continue as we go into the future. But besides NAND, all the other technologies will also transition into 3D as we go forward. Those requirements, in turn, translate into the requirements for thinner and thinner materials that we need to deposit and develop, which basically means that we're getting into the atomic scale material engineering with angstrom level precision that our customers need to be able to put these things into production. Taller and taller aspect ratios, more and more patterning, as well as more complex packaging that's required to be able to make these devices and put them together and integrate it as fast as possible. So in a sense, when we look at the requirements, these are the things that drive our roadmap. We need to develop the next generation equipment that can deal with these types of requirements. Today, the most advanced GPUs that are produced with 4 nanometer and 3 nanometer technology in high volume manufacturing. And that relies on a FinFET technology. As we go beyond that, next year, 2 nanometer technology, which is gate-all-around technology, will transition into high volume manufacturing. And after that, the next generation gate-all-around, as well as CFETs that would come. And these will basically take us into the early part of the next decade as it happens. So today, the state-of-the-art technology that's in volume manufacturing for GPUs relies on this FinFET. So let's take a little bit of, take a look at the requirements for next generation as we go forward.
Building the gate-all-around structure requires a number of specialized atomic layer processes, such as selectively etching between the channels, one layer at a time. And using ALD to form the spacer in between them. These processes become even more difficult at the next node because the device gets taller and smaller. In addition to shrinking the transistors, the wires that connect them together also need to scale. When building such small wires, only dozens of atoms across, many things can go wrong. New EUV patterning technologies reduce these errors and defects. Another approach to scaling is to reduce the complexity of the wiring. Traditionally, the power and signal wires are intertwined. Moving the power wires to the wafer's backside reduces congestion and improves performance. This requires even more copper plating. Back at the transistor level, the CFET inflection will require even taller structures and additional wiring with more deposition and etch, which will enable the logic scaling journey to continue to the point where there are more transistors on a single chip than 50 times the number of pizza slices eaten in New York City in a year.
So that's what's coming to us. This is the roadmap, at least that our customers have until the end of this decade and beyond that. FinFETs will probably go into production by early 2030s. And one thing that you notice is as we move from FinFET into gate-all-around and after that to CFET, you saw how the structuring is done. But you see that the films are becoming thinner and thinner, and you see a lot of new applications that are coming in that have these acronyms of ALE and ALD. And there are multiple places where you see these things. So when we think about the future, as we try to make this transition to the next nodes, these are what we see as the grand challenges that this industry is working through to resolve. One of them is atomic scale precisions, films that need to be so thin that they're really not films anymore. They're almost interface. It's about 1 to 2 nanometers across with angstrom level precision that you need to have. So I'll talk about this in a little bit. And sustainability. How do we make what we're actually working on more and more sustainable? And last but not least, speed to solution. We need to be able to develop these solutions faster and faster than we were doing before. So there are many, many challenges for equipment industry as well as for our customers to scale. But these are the 3 grand challenges that today I wanted to focus on with you. Atomic scale precision. So what is ALE? ALE is atomic layer etching, is a technique that's been developed to be able to remove one layer of material at the time. Consider a very simple example of silicon etching. You have a crystalline silicon that's over here. If you can actually bring in halogens to the surface and run long enough time that the halogens would occupy every site that you have and give you a complete coverage, you get to a saturation regime. And you need to wait until this happens. So you need to sort of run it enough time to give complete coverage to the surface. Then after that, you bring in ions with a very controlled amount of energy to be able to just remove the halogenated layer and not enough to damage the bond that you have below that. And then by doing this, you can just remove one layer, and then after that, you cycle. It becomes atomic layer etching when you give enough time for the halogens to saturate the surface and enough time for the ions to saturate. And then you go through the cycle over and over again. When you start depositing films that are only a few nanometers, and you want to remove 1 nanometer of that, you have very little budget to be able to mess with that film, so you need to be able to remove it very, very precisely and in a controllable manner. So there are techniques, atomic layer etching, that today actually our customers run in production. Obviously, you don't need it for every application. If you don't need that level of precision, if you don't need that level of precision, you don't necessarily need to do atomic layer etching, but these techniques today exist and are in production. You can now generalize this concept to atomic layer deposition, where you can bring in 2 different precursors to the surface, one to saturate, another one to convert, and then cycle. Or you can also do the same thing with atomic layer etching in an isotropic way, that you can bring in 2 different species to the surface and be able to convert and then remove and convert and remove. Ideally, it depends on what it is that you're trying to do. Whether if you have an ALD, it is typically conformal because you deposit it very, very conformally over the whole structure that you have. So you deposit a very conformal film that has the same thickness, whether you're in a small area or large area, at the bottom and at the top. When you're doing isotropic or anisotropic or directional ALE, you're only removing the bottom and you have anisotropy, that you go down. When you're doing isotropic ALE, you remove the same amount from all surfaces and you do it in a very controlled fashion, but regardless of the spacing, without sidewall and the bottom. So we need to develop these types of techniques as we go into the next generation. Gate-all-around and 3D transistors all need these type of techniques as we go through it. So the good thing about ALE and ALD is that you can actually etch small features or large features, or deposit, in this case, to be the same amount. You can do a conformal coating, and in case of an ALE, you can etch to the same depth regardless of the opening. You can deposit it with very, very uniform across the wafer, and you can have wafer-to-wafer repeatability that's sort of angstrom level precision that you can do. But it is expensive because you have to wait for a long time to be able to do those purges. And everything that we're doing is to try to make that faster and faster, optimizing the volume of the reactor, the purge schemes, and things that we have to be able to do that. As I mentioned, all sorts of devices are going from 2D to 3D. This is an example when 2D devices today that you're doing by shrinking in 2 dimensions and printing, if you go to 3D, you basically need to still make the same device, but you make it on the sidewall. In these cases, traditionally, we have always used and relied on ions to give us anisotropy, to be able to do it from top down, but it's very difficult to get ions to go 90 degrees. So what you then need is more and more ALE and ALD. Now you need to be able to recess to a very known depth, very uniformly top to bottom, and you need to be able to deposit exactly the precise amount that you want from top to bottom. So these are a lot of the challenges that we need to work together to resolve as we go into the next generation. The good news is ALE can actually give you very good top to bottom control, but you end up needing to recess a lot of material that have to have selectivity to some other material. You may be recessing molybdenum that needs to be selective to oxide. You may be recessing silicon that needs to be selective to silicon germanium. You may be etching one material. A few years ago, Intel published this paper. It's called the 4 color problems. You want to be able to remove one color without touching any of the others. As we go into 3D DRAM, you end up with the 50 color problems. You have all these sort of materials that you need to be able to remove selectively with respect to the others. This is an area that we actually need to work together on. We need a lot of innovations. A lot of these solutions don't exist today, and we need to work together to develop these. The next one is, as you build these devices, you need to actually create the channel. You need this surface to be a channel that is crystalline level and is precise, but it also needs to have a very precise shape. In this case, actually, if you're recessing, this is from a simulation of the features, and as you can see, as you can toggle the selectivity of one material to the other, you can end up getting very different shapes. And you can control the thickness as well as the overall shape. So depending on the target profile that you have for your integration, you have to be able to tune these sorts of selectivities. Again, a lot of areas for research and innovation that needs to come in here. And you need to do all of these things while the material that you leave behind has to have atomic layer precision. That's the challenge that we're seeing as we go forward. After you have etched it, you now need to come in and deposit a film that goes into these gaps uniformly top to bottom without having any seams or any holes. And imagine this could be 6 to 7 microns deep with an opening of about 35 nanometer that you come down to be able to fill these. And you have to be able to do this. So we have developed some techniques. Like, for example, we have a technique that we deposit, we do an ALD to a certain amount. We inhibit the front so that no deposition is done here. And then the next, as you come and deposit, it fills it in from inside out. That works up to some aspect ratios. But beyond that, you end up getting these voids. So this is another area that's really ripe for collaboration and for innovation to be able to get us to the next level. There are also other techniques that could be done in order to combine etch and depth to be able to do these fills and get better. But again, as you can see, there are a lot of challenges with top to bottom, seams that are formed in here, and so forth. So, but if you cannot overcome this, 3D DRAM cannot go into production. 3D DRAM cannot go into production with these type of fills that you have here. It needs to be done, and it needs to be without any seams, without any holes, or without any voids. So I hope that gave you a little bit of glimpse of the type of processing that our tools need to do as we look into the future, and some of the challenges that we have on the atomic level scale that you have. The next challenge that I want to outline for you is sustainability. Overall, sustainability falls into 3 different buckets. The energy consumption and the direct emissions that every company has from our own facilities, the energy and the indirect emissions that we have from the energy that we purchase, plus the indirect emissions from the tools that we sell to our suppliers. So when we say we want to be net zero, we have to be able to satisfy scope 1, 2, and 3. And this is not just Lam Research. We, plus our customers from our suppliers, the whole supply chain needs to work together, because effectively our scope 3, the emission that we have from our products, is the scope 1 of our customers. If we cannot achieve net zero here, our customers cannot achieve their goals either. So the whole supply chain has to work together to bring this in. This is why it's an industry-wide challenge that we all have to work together to be able to meet. One of the challenges in this area is the gases that we use today. Some of these gases have high global warming potential. For example, gases like SF6 and NF3 have very high global warming potential. But these gases are the ones that we've been using in this industry for the longest time. For the past 60 years, we've been using SF6 and NF3 as a source of fluorine generation in this industry. And the global warming potential of SF6 and NF3 are significantly higher than CO2. So we need to be able to come up with substitutes for these gases that we can use, that our customers can do, and the whole supply chain for these gases that needs to be put online. The good news is there are cases that we have actually demonstrated this. This is one case for etching high aspect ratio holes that we developed new processes and new gases that we were able to deliver actually significantly lower emission as compared to the baseline, but at the same time delivering much better on-wafer performance for our customers. So cases like this exist, and we just need to do more of this work. Another part for sustainability, and that's why it's a big grand challenge for us, is the overall energy consumption that we use in the entire system. It's the tool that we have actually is connected to a lot of equipment in the subfab, and it could be chillers, pumps, and others that are sitting over there. And when we can develop virtual twins of the system to be able to understand where the energy is being consumed the most, and we know that thermal management, power delivery, and abatement are some of the big ones that we need to identify. And there is a lot of room for improvement, especially on the overall thermal management of multiple systems that we have here. For mechanical engineers in the audience, this is a great place to actually start focusing on and looking at how we could come up with more agile systems for improving the thermal management and reducing the amount of energy that's used in these areas. Basically making the system more and more efficient, which is good not just for the environment, but it's also good for overall reducing the energy consumption of the fabs that are running. Last but not least, I wanted to talk about speed to solution. As I presented here, the roadmaps in all the different segments of the industry are accelerating. And as we go to the next generation, the challenges are building up atomic level precision and others, and the tools that we're developing are becoming more and more complicated than they were before. There is Moore's law, which you all know. At Lam, we have something that we call Lam's law, which is every year, the tools that we're delivering to our customers to break the trade-offs, to deliver the solutions, have more knobs on the reactor. And now we have so many knobs on a reactor that we can, in order to deliver, a process engineer can dial in 10 to the 18th different unique processes on the tool. 10 to the 18th different unique processes on the tool, given the knobs that we have on the tool. So if you're a process engineer, how do you find the optimal? How do you do this optimization in a time that actually delivers a solution to our customers? One of the things that you see is that both cost, complexity, and time are going up as the overall complexity in industry is going up. So time is money. If it takes you a longer time to do it, the cost of R&D goes up. And at some point, it's just not sustainable. So together, we have to innovate, and we have to come up with ways of being able to deliver solutions much, much faster than we were able to do before. This is an optimization problem. And as we go into atomic layer deposition, atomic layer etching, we have more and more knobs, and the problem becomes more and more complicated. So one way that obviously with the introduction of AI, we're doing more and more everywhere is adopting AI, adopting machine learning, and developing a partnership between humans and machines. So what are the advantages of humans? We had an earlier discussion with Eli this morning. Humans are very good at domain knowledge, creative, and we can actually, with very little data, being able to make decisions, and we're very, very good at developing intuitions based on the experience that we have for single variable or maybe two variable optimization. But when you have so many different knobs on the reactor and you need to be able to optimize multivariate analysis, we're not very good at that. Machines are a lot better than that. Algorithms are much better than that. Machine learning is a lot better than that. So the question is, how do we form this partnership to be able to bring in the experience, bring in the intuition, be able to go together with computer, with AI, with machine learning, deliver the fastest solution that we can. So let me give you an example. Today, if you want to buy shoes, what do? You just go to your search engine, you put in that you want to buy shoes. The computer goes out there, does a survey, and comes back to you with a whole bunch of different solutions. You take a look at those solutions, and you make a decision. So this is a case where computer goes first, you ask a question, and it gathers, and then human makes a decision. When you look across the industry, we have these partnerships between humans and machines everywhere. In aerospace, every part of the airplane, engines, wings, the overall system, everything is modeled first on a virtual twin, and then after that you bring it in and you build it. So modeling is done of the entire system, is adopted and is done regularly, basically every day when you do these aerospace designs that you're doing. Pharmaceuticals. The space is very, very rich. It's very similar to the process development activity that you do on reactors that we have. So biologists first need to come in and give you exactly where you want to start with the right protein, start with the right DNA, and how you want to change it, and then after that you use machine learning in order to optimize it. Whether it's automotives, whether it's Amazon, we are seeing more and more robots that are being created and put into manufacturing. It's not just to do the job for cheaper, but it's to do it with more precision and better than for those tasks what engineers can do. So this is 3 different examples of partnership between engineers and computer, between human and machines that are being done across the industry. If you look in semiconductor manufacturing, we're also doing exactly the same things. We are also developing virtual twins to be able to model the reactor before building a reactor and cutting metal. For process development, we're also trying to accelerate our process development activities. And at Lam, we're also developing robots that our customers can use for servicing their tools. So for hardware development, more and more we're doing reactor scale simulation to be able to look at the flow, look at the plasma creation, and how the whole system comes about, to be able to model it as much as possible, designing the edge rings, designing the overall system before we cut metal, and even when we want to improve it, what can we do in order to do it better and better? We have plasma models that we use today in order to simulate the model, but these models can improve. And in fact, one of the projects that we're here with Professor Lieberman and the team that we want to work on is to actually try to see if we can work on a collaboration to enhance the simulation capability of these reactors that we have and bring in more widgets into it. For process development, several years ago, this was about 2 years ago, we developed a game to benchmark how humans would do process development versus machines. It was a very simple game that we put together. We said this is an initial profile that we would try. It's given. We would like to get to this profile. We have 10 parameters. Go ahead and do the process development. Whoever comes up with the fastest solution, the least number of experiments, would win. We gave it to a machine, and we asked a machine to do it. It actually took it about 739 steps, and it had no idea where it was to be able to converge. We gave it to an experienced engineer, And you can see that experienced engineer started out and within about maybe 15 steps got to about 80% of what their target was. And after that, you can see that it took about 80% to go another 20% to be able to converge. And it took about 105 steps. Certainly, the experienced engineer did it faster than the computer without any guidance. But it was fastest when humans started first, and after we had the directions and the baselines, using a Bayesian algorithm or any algorithm in which you would look at the slopes and the gradients, be able to converge much faster. So this partnership that you can start out with humans and then transition it to a machine in order to do machine learning process development activity is the one that's actually, in this case, gave us the biggest bang for the buck. And you can see why. We have intuitions based on the experience that we have. We could do single variable process tuning and optimization, and you can get there really fast. But when you get into this space, you have to do 4 or 5 or 6 variable optimization in order to get there. And it's very hard for people, even for an experienced engineer, to do it. And it's a lot easier for the machine to do it. One thing you do see is that sometimes the machine looks and sees that it doesn't have, the algorithm says, I don't have enough data to be able to converge. So wants to run some points that are way, way above where the target is. And sometimes our engineers are reluctant to let the machine to actually suggest and run that experiment. But it's very important to actually get that because it increases the amount of data that you have so that you can converge faster. So the problem that we have is very similar to the biologist that's doing the experiments. We don't have a big data problem. We have a little data problem. We start out with very few number of data points, and we're in this space that has 10 to the 18th different solutions, and we're trying to optimize it there. So if you have very few points, it could be an elephant or it could be a caveman drawing on the wall that you're trying to get to, and you have no idea with the number of points that you have. So this is actually real data from some work that we recently did and we published. And you can see the engineer did about 40 or 50 experiments. Then it was given to AI-assisted process development, and the process development actually worked and converged. And it was much faster than what we could have done before. So today, we're actually forming those partnerships. We're looking to see what we can do to be able to accelerate the overall process development and reduce the cycles, speed up the cycles of learning. One thing that this is in an active area of research that we're working on is if you solve one problem and if you actually have developed the baseline, you reach the target and you have all this data, how can you use that for the next project that you're running it on? This is learning and data transfer. How can big data help little data? How can one set of experiments help you with the next set of experiments that you want to do? And we are looking to do these algorithms, and this is an active area of research. We have a couple of projects that we're running with universities to be able to actually develop these techniques to be able to optimize it. But you can see that depending on the algorithm you're using and depending on the learning that you can bring over, we can transition from human to computer as opposed to at point C at point A with much less data than we had before, leveraging the previous data. This is also a work that we're doing with Professor Costas-Panos here to actually be able to do this type of development. So these type of algorithm development and overall big machine learning is also what we need to do to be able to deliver our solutions to our customers faster. So this is the other grand challenge that we have to work with. Last but not least, robots. Robots in workplace. At Lam, we have developed these robots that are actually in our customers' fabs, and the robots work around the engineers. So this is not like you just put a robot in there and you walk away. They actually work around the engineers, and they can do very, very repetitive tasks with high precision. And our customers actually want to use these more and more because the precision of placing the parts in there, the precision of doing these maintenance jobs over and over again is very, very high. And our customers want to be able to service the tool, maintain the tool, and the tool is up and it's running. And we have demonstrated first time right of 99.9% with these robots. Just the same way that in automotive, just the same way that at Amazon, you'll see more and more of these robots. In the next few years, you'll see more and more of these robots happening in here too. Again, it's not a cost issue, it's more of repeatability and precision and why it would be adopted. And this is not about taking the jobs away from engineers, it's about making the engineers more productive and make sure that we can do these things over and over again. We call these cobots or collaborative robots. And and the name of this particular one is Dextro that we have that we're running. So I hope you got a glimpse of the future and the challenges that we have that we need to work together on. And we need to form a much better partnership, and we need to be able to adopt to the AI era and be able to learn and be able to speed up the development of everything that we're doing for our development. And with that, I wanted to acknowledge my colleagues at Lam, as well as other partners that we have for putting this together. And thank you very much.
Thank you very much. Okay, we are open for questions. Okay?
Yeah, thank you for the great talk, Vahid. So regarding I think you presented two atomic layer etching. One was isotropic, the other one directional. So what controls this as anisotropy? Is it the crystallography of the material you are etching, or is it the etching process itself?
The etching process itself. In one case, you're relying on ions. You bring one type like halogens to the surface and then ions to remove it. In the other case, you're bringing in two different types of radicals to the surface, and they're both coming in isotropically. One to form one layer on the surface and the other one to remove the converted layer.
And this is why the etch there was independent.
That's correct.
Opening.
That's correct.
Okay,
Yes.
thank you.
What specific AI models were being used to improve process development, and why?
Right. We started out with a Bayesian algorithm, and it was a simple algorithm that we could use that effectively looked at the gradient and tried to converge as fast as possible. But today we're actually looking at more complicated algorithms, primarily because of the transfer learning, to be able to bring in from the previous ones. But what we have today, the data that I showed here, was from a Bayesian algorithm.
Could you talk a little bit about the challenges of maintaining the atomic level precision once you're going between the etching cycles and the deposition cycles, when these wafers travel around the foundry? How do you do that?
Yeah, I think, good question. In a lot of these cases, as I said, you don't really have a film, you have an interface. when you have something deposited that's about 1 to 2 nanometer, as you bring it out, if those films are not very stable as you expose it to atmosphere, they can oxidize, they can convert. And in the subsequent step, before you deposit something, you need to be able to remove those layers before you deposit it. So overall, in the industry, they call this queue time effect. So what's the queue time between one step to the next? And what are the techniques that you run in order to do that? Industry is using a lot of things like carrying the wafers in a nitrogen-contained area in order to reduce the exposure to air and such. But also, there are more steps that are being added to be able to manage the surface before you deposit the next layer. That's one of the reasons that the number of steps is exploding. You just need to have all these other added layers that need to come in.
Okay, thanks for your great talk. I learned a lot from your slides, your talk, yeah. So I have several questions I want to ask you. First, you mentioned the virtual twin that we can use to simulate the real-world process. So do we have some metrics? How can we measure that the virtual twin can simulate the real-world process? That's one question. And our second question is, how can we simulate the worst case? If we can simulate the worst case, so we can guarantee that the worst case performance, so we can deploy the virtual twin in several applications that can guarantee the performance.
Right. So in a lot of cases when we're doing these simulations, it depends. We do simulations on different scales. It could be simulation, reactor scale simulation to understand plasma and radicals and ions. We can do feature type simulation that we look at the feature, and we may do those simulations with a single step and be able to vary the parameters, or multi-step like etch and deposition and cleaning and things that we're doing. In a lot of cases, we're actually looking at extreme cases, which is, let's do a very, very high aspect ratio, much higher than we actually do, and if we can deliver to that, then we can deliver to our solution. So a lot of the simulations that we're doing is also what we call torture tests that we're doing in those extreme cases.
Any other questions? I'll give Eli.
So I was not expecting so much machine learning in the talk from Lam Research. When did this become a big deal at Lam?
I would say over the past 4 or 5 years, we've been getting more and more into this. Yeah, we actually have a lot of data scientists at Lam now to actually focus on algorithms and development and stuff. You know, when your R&D cost becomes more than $1 billion to $3 billion, you start looking at other ways to try to optimize it. And so AI is exploding, and it's impacting all of us. So we also have to get with the times and be able to bring it in and see what we can do to improve both cost of R&D as well as time to solution.
So a related question. So I like cobots. It's great. So but you explained that the multivariable calculus is, of course, more complicated for humans. So, and you also explained that you don't have a lot of data in this space.
Correct.
So, but is it just a question of time? So, when you start collecting this data, and at some point you will have a lot of data. So, at that point, will engineers...
The space is huge. The space is huge. And we always develop next generation tool with newer knobs that we never had before. And so you never get caught up with it.
Let me follow up on that. If I understood correctly, I think somewhere early in the talk you said that I think you showed a progression where certain processes, the total number of parameters, the size of the parameter space was as high as 10 to the 18?
Correct.
So in my simple picture, if I'm trying to understand that, that means that you have like that's equivalent to, say, having 1,000 knobs, and each knob can have 1 million different values.
Yes.
So what's the real story? I mean, how many knobs and what resolution?
Well, for example...
How do you get to 10 to the 18?
So on some of our tools, we have, for example, electrostatic chucks that have more than 100 zones for controlling temperature uniformity of multiple places. Mm-hmm. When we put some of these recipes together, a recipe may have 100 steps.
Yeah.
Each step has X number of variables that you have. And when you put them all together, 10 to the 18th is nothing. You can easily get there.
Okay, so that's
you're trying to do this
series of steps. Yeah,
correct,
okay.
Correct. Yes, we have maybe 20 different gases that are on the tool, and you may use them in different steps for different things. Lots and lots of different parameters that you have, and then for these high aspect ratio, yeah, you don't do it all in one step. The simulation I showed you here was the comparison between the engineer and the human was for one step. Yeah. But in reality, when we're doing this 200 to 1 aspect ratio, it's many, many, many steps.
Sure. Okay,
so when you put all of it together, yeah. 10 to the 18th, we get to Avogadro's number.
That makes a little more sense. So I think you said, typically a full flow process might have 800 steps.
Correct.
Okay, so that's 1,000 right there, and then each step has many parameters.
And for
then I could see how you get to 10
And for
to the 18.
one recipe, you can have
Yeah.
40 or 50 steps.
Amazing. Okay, well, fantastic talk, really inspiring, and
Great, thank you.
Gives us just a whole new perspective on what's happening in the industry. Let's thank Vahid one more time
Thank you.
for this fascinating talk.